a new topic, which will be on linear arrays. So we talked, where is it now? So far we have discussed the two major antenna constructs, which one of them it was a dipole, and the other one it was the linear, let's say, and the loop antennas. So once we discussed these two, we also had some examples from chapter 5 where we had antennas which were composed by a mixture of possible combinations of both linear antennas and loop antennas. But now we have also a new way of constructing the antennas together, which has to be used in order for us to adjust the directivity and also to adjust the gain. Now, so regarding this, we are not going to have a single antenna, which would be a dipole one, but we can have several of these, and these can be located with respect to some distance between all of the components. And because of these, now we are going to expect constructive and destructive interference of the electric field components, which means that the overall directivity of the antennas, it is going to be slightly different, or probably a lot different from a single antenna. So now, and these new antennas, which can be created by multi-elements or several elements, these are called arrays, and in most of the cases, these elements of the antenna or of the array, they are identical. So the word array, you might have heard this one in linear algebra, where a matrix is an array of different numbers. But now you can have an array of different antennas. For example, there are very complex antenna systems which can be used for astrophysical measurements, which are designed to pick up frequencies from the emission of the molecules from space, from all the arounds of the universe, or probably our solar system at least. And these array of antennas, you can watch images of these, which could be arrays of 64 or 128 antennas, which are all distributed over acres. Okay, shumë hektar, mund të ketë hektar të tëra që janë të mbushura me antena, which are all put in a plane. And the simplest type of antenna that we have talked together in the class, it used to be the loop antenna. So you can assume now having a lot of loop antennas distributed over a two-dimensional array. Now, so the total field of array is determined by the vector addition of the fields radiated by the individual elements, and this is assuming that the current in each element is the same as the one in the isolated element. Now, why do we use these arrays, or a large number of similar antennas next to each other or in proximity with respect to each other? We do this to provide directive patterns that we can selectively pick up certain directions, so that we want to send a signal at a specific angle with a very high directivity. So that's why we do it. And now, in this case, we might expect that the different electromagnetic waves, which are radiated from different components, they may interfere constructively and destructively. So they might even cancel each other. And but this perfect destructive interference and perfect constructive interference, theoretically it's true, but in practice this is only approximations. Okay, so we might not expect a pure result as the analytical solutions might provide for us. Now, several antennas can be used for different reasons, such as commercial, military applications, and the type of antennas that are used, they can be dipoles, loop antennas, aperture antennas like horn antennas, microstrip antennas, reflectors, and many more. Now, an example of this type of antennas is shown here in the figure, and here we observe a triangular array which consists of 12 dipoles. So if you count those, on each side of the triangle you can find 4-element array, and these are used to cover an angular section of 120 degrees, And this forms something which is called the sectorial array. Okay, so, and if you remember, this looks like a line antenna. It's not a loop antenna, and they are like dipoles, and you can find 12 of them. Now, another type of array of dipoles, this is this array which is shown here in this figure, where we have several line elements or several conductors which have some radius. We know now the different parameters of antennas, where one of them can be the length, the other one is the radius of the conductor. With conductors, we mean these possible tubes or metal tubes, where copper one is one of the most commonly used ones. And probably this antenna that we see here, this is something that we often see in the TV antennas that we use to pick up the TV signal. So, and this is a name. This is called Yagi-Uda array. And let's say again, the simplest and one of the most practical arrays is formed by placing several elements along a line. And initially, we're going to consider the two-element array. So after the two-element array, we're going to see, for example, how these two elements can be adjusted in order to receive different patterns or different directivities. Whenever we have these two elements, we can have even more. One important element is also how much, what is the excitation coefficient on each of these. This is in line, or you can assume this one as if you can have a dipole antenna which has some reference magnitude of the electric field or of the signal radiated. Another antenna next to it, it can have, it may not be equal to this one, but it can be twice as more powerful or 3 times more powerful. And in case different array antennas do not have the same excitation coefficient or do not have the same power, radiated power, we need to work carefully when we do the addition of all of these components at a specific distance. And when we talk about the possibility or the need to calculate the radiated power or radiated electric field intensity at some distance, we are immediately bringing back all we have learned or all we have practiced so far into approximating the distance from the center of the antenna components. Now, whenever we analyze the antenna arrays, we consider the uniform distribution of the signals across the arrays and also a non-uniform distribution. Whenever we have a non-uniform distribution, we have a whole piece of mathematical apparatus which is needed to be implemented, and what is essential for us, or what is relatively easy for us, is that nowadays, whenever we work with complex systems of arrays, which could include non-uniform signal distribution across all of the array elements, the good thing is that we can often go and refer to tables where we just read out important elements. We don't need to analytically describe all the outcomes. Okay, so a lot of theory of the antennas, it has been constructed over the last 100 years. So the mathematical tools, the apparatus, it has been out there, and it is not that, which also might point to the existence of well-constructed tables from where we can extract important information. So we can have n different arrays for antennas, but let's start from the simplest one, which is a two-element array. And two-element array, initially we start with two infinitesimally small horizontal dipoles positioned along the z-axis as shown in this figure. Now, so here we see that the center of the dipole, it is located at 0, at z equal to 0. The distance between the two dipoles is d, and let's say the point of interest where we want to calculate the fields, it is at some point P, where with R we denote the distance of the center of the dipole. R1, it is the distance of the upper dipole, and R2 is the distance of the second dipole. Now, in an approximation where R is much larger than D, okay, so we can assume that D is very small and we are at a very large distance, we can, you can draw an isosceles triangle, mund të ndërtoni një trekëndësh dy brinjishëm, where you can draw, let's say, you can draw a line between, let's say, or you can assume the following. What is the difference between R and R1? The difference between R and R1, it is equal to d over 2 times cosine theta, okay? Because you can draw a perpendicular line from where the top dipole is, you draw it to the center distance, which is R. So in principle, you just can assume the difference between R and R1 is d over 2 times cosine theta, and the distance between R2 and R is again d over 2 times cosine theta, but we can see these equations again later. Now, this is the geometry. If we are at a very far distance, this representation which is shown here, it is more, it looks better. It is going to look rather something like this in the far field observation. And probably this is more easily, wait a second, I believe I can do something like this. So if we draw a line here, and this is perpendicular, this is an angle 90. Similarly, if we draw a line here, and this angle is also 90 degrees, we can observe that R minus R1, R minus R1, this is going to be equal to the distance d over 2 times cosine theta. The same thing, so it looks like, wait a second, this is true. Then R2 is also larger by this much with respect to the R. Okay. Then let's see here. Now, whenever we have this two-element array, as in the previous slide, we're going to see that the electric field component, it is going to be a purely complex value. Okay, so always in these fields for the electric field, we might expect the following. First of all, it's going to be a purely complex quantity. That's why we see this J. The second component is that we're going to see this intrinsic impedance K. Then, for sure, it has to be proportional to the current. Of course, it's not going to be proportional to I squared. Okay, it is always going to be proportional to I to the power 1. So this is to the power 1, this is to the power 1, this is what we expect. They're going to be proportional to L. Then we expect 1 over R dependency, always there, and also the propagation constant, or the space propagation constant, which is to e to the power minus jkr. So, and then we might expect a sine or a cosine dependence of the electric field intensity for both cases. Now here we have E1 and E2. E1 and E2, they correspond to, let's see, the distance which is R1 and the distance which is R2. So let's also notice here, R1 is smaller than R, R2 is larger than R by this much, and this is considered for phase variations. The amplitude variations, we don't see much difference because since D is negligible with respect to R, we can simply say that these three will be equal. But the phase, it is something which can change much abruptly than the distance. And one important factor that we observe here is that we have a beta, which is the difference in phase excitation between the elements. Now, we are assuming that there is some beta initially. Sometimes, or often, we may observe that if we have let's say, a dipole antenna, which means that we have, two dipoles, then often we might observe that the phase difference, the beta here, it has the same phase for two components. Or we can have n components, all are excited at the same time. So there is no phase difference between the electric fields that are produced from these. So this beta, for the moment that we see here, consider this one to be any value between 0 and pi. Then this is what you observe for the total electric field which is going to be generated. E1 is right here, and E2 is this new component here. Then what we can do is that we can factor out the cosine theta, and then, sorry, this does not look very good, this slide, there is a mistake here, but I can write this on the board. So this is the tangent component, and this will be ki0 a to the power gr cosine. So this is over 4 pi r, this is cosine theta, it stays the same, and here we have 2 cosine. Here we can put here 2 cosine 1 over 2, okay? 2 cosine 1 over 2, kd cosine theta plus beta. Kd, apologies for the need to do this, cosine theta plus the beta, and okay, so this is going to be the tangent electric field component, and then often what we, and wait a second, so in fact this whole expression, this can be represented as for example, this will be the first major factor, this one here. And the second part, or the second component, we can call this one the array factor. So the factor so this is AF, okay? So this is an important factor that we try to calculate, and this carries the fundamental geometries which can be used in the antenna. So a lot of information is hidden here. Often we may be interested into having a look at the normalized version of AF. So if we have here a factor of 2, we still may be interested just into looking at how this is changing as a function of angle theta, because it is this term which is going to help us determine the directivity and also the null. So what is the null? It is the direction over which we measure no signal, because we don't often have omnidirectional antennas. Often we expect to see some directions where we have a pure null region where no power is radiated. Now, so the total electric field is equal to the element factor times the array factor. Array factor, it is this AF which is shown here. Array factor, and now the array factor is shown in detail in here, but we can normalize this one because often, as we said before, we may be interested into obtaining the information on how the wave it is distributed. Now the array factor, the AF, this is a function of the geometry of the array and the excitation phase. By varying the separation d and the phase beta between the elements, the characteristic can be controlled, so we can control them. And it's always good to remember that this factor kd, which we are going to see, we should not forget that this is k, it's always equal to 2 pi divided by the wavelength, so this is k, 2 pi divided by lambda, and then the d, we often report the d as a, I don't know, let's call this one. Let's assume that the distance, it can be expressed as lambda over alpha. If alpha is around, let's say, 0.1, that means that d is equal to 10 lambdas, right? So we can have distances which is in the order of several lambdas, but if alpha is equal to 4, then the distance between the two elements in the array, this is going to be equal to lambda divided by 4. Now, these two values, whether the relative size of d with respect to the wavelength, it is also very important because often we may or we may not even see a null region at all, which means that we may not even if we desire some null direction, which means that we expect the antenna to be located around a very narrow angle, and we might be expect the end of the lobe at some angle. We might not even observe it because we know that the sine and cosine there are values which are defined from -1 to +1, but depending on the values of d, sometimes we may not even, we may never get a cosine which should be defined between -1 and +1, but examples of this we'll see pretty soon. Now, the far zone field of the uniform two-element array of identical elements is equal to the product of the field of a single element and the array factor of that array. Okay, so this means that this is something which is nice. So we can pick up the field of a single element, we multiply with the array factor, and we get the complete emission or radiation of for the antenna. The array factor, the AF, is a function of number of elements, geometrical arrangement. So geometrical arrangement here, we observe that it depends on D, okay? D, which is the distance between the components, the relative magnitudes. Now, the relative magnitudes, this is important. I think I just mentioned this one just once so far, is that the amplitude of the field, it may not be equal in all components. In one of them could be 4 times more significant than the neighboring component, and so on. It depends on the relative phases. The relative phase is the beta, and their spacings. Actually, the spacing, it is this D that we see here. The array factor will be of a simpler form if the elements they have identical amplitude, phase, and spacings. Since the array factor does not depend on the directional characteristics of the radiating elements, it can be formulated by replacing the actual elements with isotropic point sources. Okay. Now, let's assume that we have, so this is just an example. Let's assume we have an array which has 2 components, and we are given a distance d and some beta. And then the electric field tangent component normalized, so Tn, this means that it is going to be normalized. We just want to see the angular distribution rather than the amplitude. So that's why we see this n. And this can be described as cosine theta times cosine 1/2 times the rest of the terms that we see here. Okay, and then here we are. Yes, and now this we can analyze what goes on with this antenna by assuming different conditions. When the distance between the components, they can be described as λ/4. Then the phase difference between the 2 subsequent components can be 0, can be pi/2, and pi divided by 4. I just want to apologize just for one second. Sorry, apologies just for a second. We'll go back to here. So now we have this D, and then we're expecting to find how does this AF factor, how this depends on this D. So here we have K, it is equal to 2 pi over lambda, D is λ/4. So we can simplify these terms here, and then we can observe that we get here 1/2 times pi/2 cosine theta plus beta. And then, so the overall, it looks like once we are given this specific value, we get a normalized AF factor as shown here on the figure. This can be simplified a little further depending on the value of beta. So we have not substituted yet what is this beta, which is the phase difference between 2 subsequent components of the array. And let's see what we see. So let's assume beta is equal to 0. If beta is equal to 0, then this whole expression for the normalized version of the electric field, it ends up being cosine theta, cosine, so we get cosine theta that's here, and cosine, so this will be gone if it is 0. This is kd cosine theta, and this is pi over 4 cosine theta as shown in here. Now, we may be interested into observing where the null directions are. For this one, we can equal this to 0, okay? So if the first term is equal to 0, it doesn't matter what the second term is for sure. And we know that cosine 0, it is equal for whenever, okay, so it looks like I don't see this here, but we know when cosine is 0. Cosine, it's 1 here. It is minus 1 at an angle of 180, but cosine is 0 at pi over 2, and also at an angle of theta minus pi over 2, okay? So we have two regimes where this is possible, where this can happen, okay? So then, wait a second, so here we are, we get pi over 2. Then we have the second condition where now this can be 0 or the second term can be 0, and again cosine pi over 4 cosine theta can be equal to plus pi over 2 or minus pi over 2. So because let's not forget, we had cosine here, right, and cosine here. In this case, we can just simplify the pi's here, and it looks like the cosine theta, so imagine for a moment, cosine theta is going to be equal to 4 divided by 2. So this means that cosine theta is equal to 2, but this is never possible, okay? So it's never possible that the cosine theta can be larger than 1, because here we see, anyway, I think it's obvious. So apparently this is gone, but does not exist. Doesn't. Similarly, we can also observe whenever this angle is minus pi over 2, we cancel out these terms and we get cosine theta and is equal to minus 2. Again, this is not defined, okay, so these are gone, which means that we can, if we have two array components or two antennas, dipole antennas, which are far away from each other, lambda divided by 4, and the phase difference between these two components is equal to 0, we can observe a null space only for pi equal to 2 and pi equal to negative, when angle is theta is pi over 2, and let's remember, what was theta? Theta, it is this angle, okay, so this is theta. So it looks like we can observe a 0 at pi over 2 and minus pi over 2, so we might observe such an antenna distribution. Maybe it's better if we draw it here. So we should draw it here. Now the angle theta, this is the angle theta. So that means that if we get a 0 at pi over 2 and minus pi over 2, that means that the antenna can have a distribution which is going to look like this. Okay. Let's move ahead now, for the moment, we have an equation here which is essential, but we may not understand this one directly because, we are going to come back to this slide again when we analyze not only two components but many more, because the array factor maybe is best. Let me see for a moment. Okay. So the array factor, it is in fact, let me do it here. So AF, if we have several terms, this is equal to the summation from 1 to n. Okay, so let's assume we have n terms, but for sure here n is equal to 2. And here this is exponential, which is e to the power jn minus 1. This is j. This is very difficult to write it like this. It's really difficult, j minus 1. And then here we have some other terms, okay? Now, for a moment, j n minus 1 times kd cosine theta, and so on. So this is exponential. So let's assume for a moment when n is equal to 1, the first term, it is 1 minus 1, 0. So the first term is 1. So in the AF factor, in the array factor, we are going to have 1. So this is equal to 1 plus e to the power. Now, when n is 2, 2 minus 1 is 1. So this here we get e to the power j k d. Okay. Now this kd, this was equal to pi over 2 based on the previous results we did here, right? So kd, it was equal to pi over 2 because d was lambda over 4. So this is why we see this calculation here. But as I promised to you, we are going to see this once again. And by the way, yeah. So, and let's see. So when d was equal to lambda over 4, the element, it has this distribution, the array factor, this is what it's going to be. And actually, the array factor, it is, yeah, let me think for a moment. And then we have to multiply this expression by the array factor. And finally, we get this distribution that looks like this as a function of the angle theta. So we said that we're going to see a null or a direction where the intensity of the wave is 0 for theta equal to pi over 2. If you assume that the antenna is going to look like this, one dipole here and one here, and the z, it's pointing up like this, and the angle of interest is angle theta here, the distribution, I can draw this again, is going to look like this, okay, and like this. Which is actually what we are really seeing here, but I was just trying to, so this is showing actually the angle theta is changing this way or this way. Okay, good. This was when beta was equal to 0. Now let's consider another case when the distance between the two antenna elements, it is lambda divided by 4, and the phase difference between, and by the way, let's just check. Do you have any questions so far? Can someone answer using the microphone? Do të sigurohem që po më dëgjoni ose?
Professor Josh.
Faleminderit që më konfirmove. Okay, thanks. So we are assuming again when the distance between the two antenna elements is lambda over 4, and the phase difference, so far we did it when beta was equal to 0. But now let's assume that we are producing two radiations from the two antenna components, but with a phase difference which is pi over 2. In that case, if you remember, this was kd cosine theta. So just have a look at this equation. This was kd cosine theta, and this was plus beta. Okay, so just we just need to go back for a moment. This is, so just have a look at this expression. Now, beta is going to be pi over 2. Okay, so we are assuming beta is equal to pi over 2 divided by 2 is going to be pi over 4. So that's why we see this pi over 4 here, and we want to observe how the power distribution is for this specific antenna. Let's try to find the nulls first. So let's try to determine the null, which we spelled it like this. So we want to make this first 0. When is 0? This is 0 when the angle is pi over 2 or 3 pi over 2. Now we consider just pi over 2 since we calculate the angle z using a specific symmetry. So this goes from 0 to pi, okay? So we never go 3 pi over 2. So it looks like we are going to get a null right here as we got in the previous case when beta was equal to 0. So when this term is 0, we found it what it is. Now we have to look for what angle theta this whole term is going to be equal to 0. This whole term is going to be equal to 0 whenever this angle is equal to pi over 2. So let's equal for a moment. Let's assume that this is equal to pi over 2, and we get these terms. Actually, it's clear. Let's assume that we want this. Okay, and what we do here, we just cancel a lot of the pi's here. There are too much. We multiply by 4 everywhere, and what we get the following. Cosine theta n, this is equal to, or cosine theta 1 n plus 1 is equal to 2. So imagine for a moment, we have cosine plus 1. This is equal to 2 or equal to minus 2. Okay, if we multiply, so this is, we get it from here. Now, cosine theta, that means that it is going to be either 1 plus 1 is equal to 2 or minus 3. So for the first case, this means that here we talk about cosine theta being 1, and here cosine theta, it is equal to minus 3. Now, this is possible. Cosine theta can be 1, and this happens when theta is equal to 2 pi n, okay? And so this is what we are saying here, actually, so, or 0. So cosine 1, it happens when the angle is 0, but we don't consider 2 pi. Why? Because you should never forget that theta, it goes from 0 to pi. So this angle, it is pi over 4, right? This angle here is pi over 2, and this is pi. Good. So we get stuck here, and then when the beta is equal to minus pi over 2, we get cosine theta is equal to minus 3. This does not exist. We forget it. And then we can also obtain, when cosine theta is 5, this is not possible, but it looks like we can observe null of the power distribution for pi over 2, which is this 90 here, and also for this angle 0. So these are the only two cases when we do observe the null for this antenna distribution. So again, wait a second, I believe, so let's go back. This was 90 and 0. This is true. So the antenna distribution, it is going to be a null in this direction, okay, and in this direction. So that's where we observe nulls, but we don't observe a null around here. This happens at this specific angle distribution. Let's consider a third case when beta, so let's not forget, so far in the second case, this was beta was pi over 2. So here beta it's pi over 2, now it's minus pi over 2. In this case, we're just going to carefully substitute all the numbers which we have been provided. We want to zero this distribution of the electric field. It can be 0. We know that this term can be 0 at this angle theta, but then the second term, it can be equal to 0 when all these are equal to pi over 2, okay? Similarly, we cancel out these pi's, we multiply by 4. When we multiply by 4, we get that the cosine minus 1, this is equal to 2. And now, similarly, we can observe that this is possible only in one specific case when the angle is equal to 180 degrees. So let's check it again. We're going to have a 0 at theta equal to 0. So this looks like at the top. When we say at the top, we consider that whatever the way the antenna is going to be no. If we have another antenna which is going to try to pick up signals right above the emitting antenna, which is composed of two elements, this is not going to measure anything, okay? And also, if we put another receiving antenna at the bottom, but let's see this one. This is beta minus 90. Wait a second, I have, no, I was wrong. I said that not when we're at the top, when we're at pi over 2. So let me repeat. So we got 0 at this angle, so at these two values, right? Yes, 90 and 180. And this is wrong. Don't look at this, please. Look at this. 90 and 180. This is mistake. So this looks like, if we have an array of antennas, which is going to look like this. This is a dipole, this is a dipole. The distance between these two, it was lambda divided by 4. Let's see what it was. The distance, it was lambda divided by 4, depending on the wavelength, that it's a quarter of a wavelength. And when the phase difference, it is minus pi over 2 between the two. So this means that this is going to emit a signal by with this wave. The other one, it is going to be shifted by a phase angle pi over 2, and wait a second, minus pi over 2. What does pi over 2 means? Pi over 2, let's try to understand this one. This whole wave, this is 2 pi, right? You can correct me if I do any mistake. Wait. No. So this is 2 pi. Then this is pi. Okay. We need a shift of this is pi. We need a shift by how much? By pi over 2. So this means that this positive side that we see here, or this maxima, this is pi over 2, this maxima will be brought right here. Here. So the half is going to be somewhere here and here. But it's going to be with a negative sign. Let's try to observe this one. This is going to be, yes, so yeah, I believe this is correct. So the shifting, this is how it's going to be. So this is a shift of pi over 2. And in this case, where I have one dipole here, another dipole here, at this distance, we are going, if we put another receiving antenna right here, let's assume that we put a loop antenna here. We want to pick up the signal that's coming from here, so this is our antenna, right? And we want to construct a loop antenna to pick up a signal. If we put this one at this angle 90, we get nothing. We get 0. We get no signal. We cannot measure the communication. And also, if we put another loop antenna here at the bottom, at an angle of 180, let's not forget, this is 180, still we pick up no signal. So we cannot listen to an antenna which is speaking or which is radiating emission using this construct. If we go backwards, I think, yeah, that's the logic. Now, this was an example of two-element array antenna, which are both infinitesimal horizontal dipoles. Now, let's assume that we have several elements, n of those, not only 2, but that we have many. Whenever we have many like this, let's also assume for a moment that all of them, they have identical amplitudes. They don't always have it, but let's assume this is what they have. But each of them, they have a succeeding element that has a progressive beta phase lead current excitation relative to the preceding one, which means that if we measure the phase with respect to this element here, the next one, it will have a phase difference beta. The next one, it will have a phase difference 2 beta with respect to the first one. The third one, it is going to have a phase difference equal to 3 beta, again, with respect to the very first one. Yeah. So we just assume all of these, and then this array that can have identical elements of identical amplitude, magnitude, but that has a progressive phase difference. This is considered like a uniform array. And again, it's a good thing that it's written here. We can observe that the difference between subsequent antenna component, the phase, let's consider this one as a reference, okay? This one, the difference, it is, well, let's use this as a reference. This is 1, this is 2. If you go from 1 to 2, the difference is beta. The path length scale, it is different by d cosine theta, okay? comparing 1 with 3, the path length difference is going to be d cosine theta plus d cosine theta. So it is twice this, right? The difference in phase between 1 and 4 is going to be 1, 2, 3, and so on. So each time we have this path length. So each subsequent antenna component, they have a phase difference equal to beta, but at the same time, they are different by this much. Now, do you have any question for what we did so far? If you like, we can have a very short break.